Given that the material exhibits a natural specific capacity of 60 mAh Hg superscript 1 at 0.83 C during testing, what factors might be responsible for the discrepancy between the theoretical and practical capacities, and how might rate capability, utilization efficiency, or ionic transport limitations play a role? How does the use of a 1M903 electrolyte affect the overall electrochemical performance by providing a medium average potential, and what influence does the electrolyte concentration and composition have on ionic conductivity, interfacial stability, and cycling performance in these sodium-ion batteries? How can understanding the relationships between synthesis methods, chemical composition, redox activity, and the choice of electrolyte help guide further improvements in the design and optimization of Prussian blue analogs as high-performance cathode materials for sodium-ion batteries? Can Davis Syringe manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the structural configuration of NiFA-PBA, ZnFA-PBA, and CuFA-PBA demonstrate the characteristics of a single NOS site within the Prussian blue analog framework? And what are the underlying crystallographic features that allow for the specific ion accommodation? In what ways does the nature of the transition metal, whether it is nickel, zinc, or copper, affect the coordination environment around the sodium ion? And how do these variations influence the overall ion diffusion pathways and the electrochemical behavior of the material? How can the differences among these three materials be correlated with their ionic conductivity, capacity retention, and voltage profiles when used as cathode materials in sodium-ion batteries? What is the role of a single NOS site in facilitating reversible sodium-ion intercalation and deintercalation, and how does this mechanism compare to those observed in materials with multiple NOS sites or more complex ion pathways? How might advanced characterization techniques such as X-ray diffraction or electron microscopy be used to confirm the presence and stability of these single NOS sites in NiFA-PBA, ZnFA-PBA, and CuFA-PBA? And what experimental data would strengthen our understanding of their ion conduction mechanisms? In what ways can the insights gained from studying these typical single NOS site materials guide future modifications and optimizations of Prussian blue analogs for the development of high-performance sodium-ion batteries? And what challenges might arise when attempting to balance high capacity with structural stability in these systems? How does the NiFA-PBS material perform with a working potential of 0.59 V? And in what ways does its ability to be charged and discharged at a density of 41.7 C, along with its long cycle life of more than 5,000 cycles at 8.3 C, demonstrate exceptional rate performance?